Okay, welcome to lesson 20. We're going to talk about sampling variability and distributions. So for instance, when we talk sampling variability, the idea is if we were to repeatedly sample, we want to acknowledge our first sample might be different than a second or a third, and so on. That from sample to sample, characteristics such as the mean or standard deviation, they'll fluctuate from sample to sample. So inferential statistics, the whole point of stats pretty much is if we do it correctly, we can take information from a sample and make a statement about a greater population. It's the whole object. If we weren't able to do this, we probably wouldn't sample because sampling wouldn't be useful. So we're going to start with a population that we have a question about. So what is theta? So remember, this is like a generic notation for a parameter value of interest. This could be, what is the population mean? What is the population proportion? And so on. So once we have that question, we're going to go ahead, take a random representative sample, and from that sample, we're going to calculate the sample version of what we're interested in. So we'll calculate theta hat. So if I'm interested in the population mean, here is where I am calculating the sample mean. And then I am using what I saw in my sample to make a statement back to that population. Things that are important to note here, though, we want to know how good using our sample statistic will be at estimating our unknown population characteristic. So, like, how good is X bar at estimating mu? That might be something we want to ask ourselves. So we want to definitely consider how the data were collected, how are they sampled. We want to consider sampling variability as well as sample size. If we have a sample that's too small, a lot of the times it's very difficult to find that your estimation is very consistent from sample to sample. So we're going to start out here with a population. The population that we chose, it's a normal distribution, and it has parameters mu and sigma. So mu and sigma here. So I simulated this. So the mean here is 50. It's where it's centered. And standard deviation is 10. And I'm going to go ahead, I'm going to take a sample from this population. So this could be sample 1. So I took a sample of 10 from this population, and I get a sample mean and a standard deviation of that sample of 10. Suppose I want to take another sample of 10. So here's my second sample of 10. So I took 10 again, but this time I have a slightly different sample mean and a different standard deviation. So you can see that from sample to sample, I didn't get exactly the same values, which means I didn't get exactly the same mean and standard deviation. And I can keep repeating this. So this is my sample 3, sample 2, and I can keep going. Sample 4. And if you look, so one thing I am keeping consistent is the number in my sample every time. But one thing that does fluctuate with every time I take a new sample, a new random sample, the mean and the standard deviation change up just a little bit because I didn't take the exact same observations in each sample. So sample to sample, there are some fluctuations. So once again, where we're coming from, we're going to start with our population, have a question. Usually it's going to be, hey, what is the value of a specific population parameter? We're typically going to be looking at means and or proportions in this class. There are other parameters people might be interested in, but those are the key ones that we're going to look at. Eventually, weeks 8 and 9, we might also look at like slope coefficients, but not here, not yet. So you take a random sample, you're going to go ahead, you're going to calculate the sample version of it, the sample statistic, and you're going to repeat this. So take a random sample, calculate the sample statistic. Take another random sample, calculate that sample statistic. And then you can go ahead and plot these sample statistics. So repeated sampling and calculating a sample statistics. And hey, look how that's shaped. So things that are really nice here. So the sampling distribution of the statistics of theta hat. So most of the time we'll be looking at the sampling distribution of p hat or x bar. Particularly this week and next week we'll look at x bar. So it'll be the sampling distribution of like x bar. So if I took every single unique sample of whatever size that you pick from that population and calculate the sample mean from all of those unique samples and put those sample means into a distribution, that is the sampling distribution of x bar. You can describe where it's centered by mu of theta hat or mu of x bar, and you can describe its spread by sigma of theta hat. Oops. So there are some statistics here we really like to use a lot. P hat is unbiased for p, x bar is unbiased for mu, and s squared, or variance, is unbiased for the variance. When we say they're unbiased, that means on average we'll get the value of that population parameter we're interested in, which is usually what we're interested in calculating or estimating. Things to note, technically S is biased for sigma, which is one of the reasons we have a tendency, we really love the variance in particular, because if we can find an unbiased estimate for the variance, we can get to finding a good estimator for the standard deviation. So you can think of statistics as random variables. The idea is if I took a sample 1 and calculate the sample mean, and then I take another sample, sample 2, I have a second sample mean, and so on. The sample mean can fluctuate from sample to sample, so it's a random variable itself. So here we're going to look at, this is my population still, so we have mu is this 50, sigma is this 10, it's normally distributed, and when I repeatedly sample, so I take all the unique samples of 10 from this population that I possibly can, and I calculate the sample mean from each one and plot them, they are going to be centered at 50, which is the population mean right here. And my standard deviation is going to get smaller. Because one way to think about it is the bigger your sample size is, here this is almost like every single unique sample of 1. Here, this is every unique sample of 10. So from sample to sample of 10, the average is going to fluctuate more than every single unique sample of 1. So things that are really handy to know about that sampling distribution of x bar. So sampling distribution of x bar. It is going to be centered at mu, which is really useful. And it's going to have a standard deviation of approximately sigma of x over root n. So we can talk about where it's going to be centered and roughly how it's going to be spread, which is really useful. So I'm going to go ahead and do a small scale example to kind of show you what I mean about a sampling distribution of x bar. So as you can see, I spent all night coming up with these numbers, right? 2, 4, 6, 8, right? I'm joking. So I have a room with 7 people in it, and they have on their torso, because why not, ages. Obviously, they're not drawn to scale. So I have a 2-year-old, a 4-year-old, 6-year-old, 8-year-old, all the way up through a 14-year-old. There are 7 people. I'm going to consider these 7 people as a population. These are the 7 people in the room. So when I want to calculate my population mean, that means I just need to find the average age of all 7 people. So mu of x is going to be 2 plus 4 6 plus ... plus 12 plus 14. And then there are 7 of them. Give you all a second there. This should be 8 years, because their ages are in years here. And one way 8 is smack in the middle. The average of 6 and 10 is 8. The average of 4 and 12 is 8. Of 2 and 14 is 8. I very much did that so I could do that math really easily. So the average of the population here is 8 years. Now I'm going to try taking a sample. I'm going to take a sample of 3 people in the room. So a random sample, 3 people in the room. I'm going to look at their ages and find the average age of those 3 people. So here's my first sample. So I'm looking for the average of sample 1. I'm going to go ahead and just put a 1 here because it's the average of my first sample. So 6 plus 8 plus 10. This one divided by 3 is also fairly easy for me to calculate. It should come out to exactly 8 years. Think about it. 6 and then 10, average is 8. 8's smack in the middle. Should be what, 24 divided by 3 is 8. So now I'm going to take a second sample. So I'm going to randomly sample 3 people again from this room. Look at their ages. So now I have the 2-year-old, the 14-year-old, and the 12-year-old. So if I want to find the sample of this group, I'm going to add their ages together and divide by the number of people, so 3. So it should be what, 28 divided by 3. It's going to be, I'm going to round here, 9.33. It's 3 repeating. So here it's rounded if you don't do the repeating. So I've done this now for 2 samples. I took 2 random samples of 3, and I calculated the sample mean for each one. So what I can do, because my population and sample size are both relatively small, I can find every single unique sample of 3 children possible, and I can calculate the sample mean for each one of those samples. And when I do, I can put those together, and that will be the sampling distribution of X bar for this particular scenario. So here, like, I went ahead and went, oh, well, if I took the 2-year-old, 4-year-old, and 6-year-old, the average in that sample is 4 years old. And I went ahead, I took every single unique sample of 3. You can tell I had to shorten their legs a bit and make their heads a bit smaller. But this here, these are a list of all the unique samples of 3 children. So this is, saying, hey, if I had the 2-year-old, 4-year-old, 6-year-old in any order, this is their average, and so on. And so I have a list of all the unique samples I could take, as well as all the unique sample means I could get. So I'm going to take all of these sample means, and I'm going to put them into a plot. So we didn't explicitly talk about this particular plot when we were talking about quantitative plots earlier. You might notice we like to have really simplistic names for our plots, like box plot, bar plot, whatnot. This is a dot plot. I'll let you wonder why we call it a dot plot. Maybe because we use dots. So I took all those means from that last page and I put them into a dot plot. And things to note is where it's centered. Here, mu is equal to 8 years. That is where this sampling distribution of X bar is, sampling distribution of X bar is going to be centered at mu, which is 8 years. So we are showing a scenario where we do know the population mean and we do know characteristics about the population to show that when we do sample and take all the unique samples and take all those averages from those unique samples, it will be centered where we want it to be at 8 years. So suppose I have two researchers, new scenario, and they're really, really interested in estimating the average tree girth in a stand of trees. Researcher 1, they go out there and they take a random sample of 10 trees. They take these 10 trees and they measure the tree girth. So how big around the trees are. Probably they have to set at a specific height from the ground. Researcher 2, they go out there and they take a random sample of 1,000 trees. Now we want to consider which of these samples are more likely to give us a better estimate of the average tree girth for the whole stand of trees. So I'll give you a moment to think about it, but hopefully we're on board with researcher 2 is probably going to get a more consistent estimate there, probably consistently closer to that true average, right? Researcher 1, if they get a weirdo tree in there, one that's extremely scrawny or one that's extremely thick, like it's going to totally throw their data set with only 10 trees in it. So we have this really fun property that we like to use, the law of large numbers. So it's saying as our sample size gets bigger, the statistic is going to get closer and closer to that true population parameter. So one way to even think about it, you had 7 children. We sampled 3 children and took the average. The idea is as we take bigger samples, so as we take closer and closer to 7 children in our sample, we're going to get closer and closer to that true average, which is absolutely true. If you sample all 7 children, you're going to get the population average. If you randomly sample 6 children, you're going to consistently get closer to that population mean more of the time. So more formally, theta hat, it's going to converge in probability to theta. In our case, what we're going to use over the next week, x bar is going to converge in probability to mu. So watch out. It's not a guarantee that having a bigger sample size means that your data are more accurate. A larger sample size alone doesn't guarantee because there's just natural fluctuation. Like you take a random sample and it just might be a poor sample. You might have gotten a sample that had some extreme outliers or something like that. So as you can see, there's some fluctuation here. They're increasing the sample size, and we have the scenario where the true mean is 50. It's depicted by, I don't know if it's a red or an orange line here, but there's fluctuation around here. So it doesn't just completely level off, but as the sample size gets bigger and bigger, the fluctuations, they stay closer and closer to the line. It does not mean that, like here, I have this sample size and my sample mean was further away than, some slightly, like here, actually, that's where the arrow should go. My sample size is further away than, my sample means further away from the population mean than when I have this smaller sample. And that's just natural, like fluctuation. It's not guaranteed a bigger sample size will get you there. Usually it's a safe bet that it's going to improve your chances of being closer. So looking at sample size and sampling variability. So as you increase your sample size, the variability of your sampling distribution decreases. So one way to think about this is the variability from sample mean to sample mean when I'm taking samples of 3 children, that's going to be more variability than the sample mean from sample to sample when I sample 5 out of the 7 children, right? The sample mean will be more stable from sample to sample of 5 than sample to sample of 3. That's the idea. So the variability that we talk about for the sampling distribution, we call it the standard error of theta hat. So it could be the standard error of x bar. So we tend to denote it SE x bar or sigma x bar. A lot of the times, we're not too worried about the distinction. What we're going to look at this week is more of theta of x bar. That's when we actually have information about how the population is spread. SE of x bar is strictly when we only have sample information. So things that are nice, as the sample size gets closer and closer to the population size, the spread goes down to 0. And you can relate this back to the population of 7 children in a room. If I take a sample of all 7, the average is 8. If I take a random sample of all 7 again, the average is 8. By the time I take a sample that's the same as the sample size, the population size, there's going to be no variability. It's just going to be the population average over and over. That's the idea, that you're going to get closer and closer to it, more and more consistent, the variability is going to go down. So definitely we have this cool simulation. I hope the link is working there. Let me know if it's not. Sample size and sampling variability. So we're still going to be working with this particular normal population that has a mean of 50 and a standard deviation of 10. If I go ahead and I take all the unique sample sizes of 10, I'm going to get a sampling distribution of x bar that's centered at 50, and then I have a standard deviation here. If I increase my sample size to 30, so I take all the unique samples of size 30, it's still going to be centered at 50, but look at the spread, it becomes smaller. So I'm still at 50, but my spread is going down. If I increase my sample size to 100, I'm still centered at 50, but my spread is even smaller. And so on. You could probably change your break size so it doesn't look like one bar, but the idea is now I've increased to 10,000. It's the spread is very tiny, and that's one reason that a lot of people, they really prefer larger sample sizes, because they do give more precise estimates. That is definitely a very common goal. Not always doable. It totally depends on what your population is and how you can reach them. But we definitely love our big sample sizes when we can. So here are the distributions we're going to be talking about. And it's not going to just be this week. It's going to be really building from this week, and we'll be continuing to use this. So you're going to have a population distribution. So here, this is the one we've been talking about. We have a mean of the population. We have a standard deviation of the population. We use capital N to denote how big the population is. So any information we have about the population is considered a population parameter because it's describing the population. Then, this is where I took just one sample of 10. So I took one sample of 10 from this population, and I get a sample mean. So here in this sample of 10, so little n because it's a sample, I get a mean of 52.7, a standard deviation of 9.7. The numbers described here, these are statistics because they're about a sample. So statistics describe attributes of a sample. So it could be the mean, standard deviation, so on. Then, if I were to repeatedly take every sample of size 10 I possibly could from this population and take the sample mean from each one, I could put it into a distribution. It's going to be centered at 50, which is the average overall, and this spread is going to go way down. It's going to be very tiny. So the value here, this is going to be mu of x bar, which is equal to mu of x, which is 50. And then sigma of x bar is going to be the population, standard deviation divided by square root of n. Is going to be smaller than it was over here. So, unfortunately, it's not likely that we're going to be able to view all three of these distributions. Typically, The sampled distribution is the only one we actually get to observe. We would love to have the population distribution, and we would love to have the sampling distribution of X bar. Both of those two distributions, though, require us to have access to the entire population, which we frequently don't. We definitely have the ability to estimate the sampling distribution, but most of the time we don't get to have the true sampling distribution of X bar, because that, if you had to go out there and take every single unique sample of 10 from a population, you'd be out there forever. It's very difficult to do. So, cautions, sampled data means I'm looking at one sample. Sampling distribution of X bar means I'm looking at all the unique samples of whatever size, and I take the sample mean or the sample proportion, something like that. And typically, the only one we actually get to see in real life is going to be the sampled distribution. So that's it for lesson 20, and we'll pick up again lesson 21, central limit theorem.